In this lecture, we are going to implement what we've learned in the previous lectures. That is to say, we're going to use a hidden Markov model to model a sequence of stock returns and find their low and high volatility regimes. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As always, you can check the lectures, how to code by yourself, and how to practice for a more in-depth discussion. If there's anything in this lecture you didn't understand, or you think I missed a step, or didn't explain why we were doing something, please use the Q&A to inquire. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Okay, so as mentioned, the library HMMLearn is not included in Google Colab. However, it's very easy to install using pip, so that's what we'll do. Next, we import the HMM module from the HMMLearn package. Next, we download the SPY dataset. Note that this analysis could work for univariate or multivariate time series. However, I think a univariate time series is more clear. As always, you're encouraged to try out a different dataset as an exercise. Next, we import pandas, numpy, and matplotlib. Next, we load our dataset into a data frame by calling pd.readcsv. Next, we call df.head to remind ourselves about what is inside our data frame. As you can see, it's just the standard open, high, low, close, and volume columns. Next, we calculate the log returns by taking the log of the close column and taking the first difference. We assign this to a new object called returns. Next, we drop any missing values by calling dropNA. Next, we plot a histogram of our returns to remind ourselves that what we are working with is a fat tail distribution. It is tall and skinny, unlike a Gaussian. Next, we create an HMM object. In our case, we would like a Gaussian HMM because our observation distribution is a Gaussian. Note that we pass in some arguments to the constructor. First, we have n components, which refers to the number of hidden states. In our case, because we know what we are trying to model, the number of states is easy to choose. In other applications, you might use other hyperparameter selection methods, like the AIC and BIC, or cross-validation. We also set the covariance type to diag, although this is not necessary in our case. The reason we want to do this is a bit outside the scope of this course, so you can ignore my explanation if you wish. Okay, so as mentioned previously, in general, we can have a multivariate time series. Of course, if our time series is multivariate, then the Gaussian distribution will also be multivariate. And as you know, the multivariate Gaussian distribution has a mean vector and a covariance matrix. This is opposed to the univariate Gaussian, which just has a single scalar value for the mean and a single scalar value for the variance. Now, if you look up the formula for the multivariate Gaussian, you will notice that it includes the inverse and determinant of the covariance matrix. These are analogous to the univariate Gaussian when we divide by the variance. So what happens? Well, there is a scenario where all your data points can be clustered very close together, which results in what is called a singular covariance matrix. Basically, the scalar analog of this would be when you have a variance equal to 0. As you know, dividing by 0 leads to numerical stability issues. Therefore, we would like our variance to not be 0, and we would like our covariance to not be singular. One way to avoid this is by using a diagonal covariance, which means that instead of having a full d by d matrix, we only have d individual variances for each of the d dimensions. That is to say, the covariance matrix is diagonal, meaning that all the off-diagonal values are 0. This in turn makes it much easier to calculate the inverse and the determinant. In any case, this is not super relevant to this code, since we are currently using only a univariate time series, and so there is no covariance matrix. Internally, however, HMM-Learn is using a multivariate Gaussian. It just happens to be a very common and sensible choice to use the diagonal covariance option. Okay, so next, we create our dataset, which is easier to work with as a NumPy array. So we take the returns, call toNumPy, which converts it to a NumPy array, and then we reshape it to be an n×1 matrix. As you recall, in machine learning, we generally work with two-dimensional datasets, where the last dimension is the feature dimension. This should be simple to understand at this point, since we've seen other models in scikit-learn which behave the same way. Next, we call model.fit, which finds the parameters of our model. Next, we do inference with our model by calling model.predictx. As you recall, this runs Viterbi and returns the most likely sequence of hidden states. So if we print out the states, we see a bunch of 1s and 0s in an array. So what does this mean? Remember that we are doing unsupervised learning. Therefore, the states inherently have no meaning, and it's up to us to assign meaning from what we observe. This is just like models like k-means clustering. When you do clustering, your clusters are just 0, 1, 2, and so forth. You don't inherently know what the clusters mean, you have to look at the data. Only by looking at the data can you see things like cluster 0 means small, cluster 1 means big, and so forth. Okay, so how can we assign meaning to these states? Well, one idea is to simply plot the sequence of z's as if it were a time series. That is, a time series of 0s and 1s. We can plot this along with the original stock returns to see if there's any pattern. So we start by calling plt.subplots and making a plot of size 10×5. Next, we call plt.subplot 211 and we plot z. This makes a 2×1 grid, and we plot z in the first position. Next, we call plt.subplot 212 and we plot the returns. This means that we plot the returns in the same 2×1 grid in the second position. Okay, so let's look at the result. So we can see that there is, in fact, some kind of pattern. When we have large values in the returns, we tend to see thicker lines on the z's. When we have small values in the returns, the z's look pretty sparse. Okay, so this is an encouraging result. It tells us that our model can in fact tell the difference between the two regimes. It's important to remember, however, that the chart on the top is not shaded in. That is, dark does not mean high, whereas light means low. Remember that the state values can be 0 or 1. So as an exercise for now, think about what it really means for an area to be dark or shaded in. I'll explain this later in the lecture, but for now, it would be a good exercise to consider this on your own. Okay, so in the next step in this script, which I think will be helpful to visualize our results, we will color code the time series instead of just plotting the states themselves as a time series. That is, we're going to plot the returns, but when we do so, we're going to make the values that belong to one state one color, and the values that belong to the other state a different color. So let's start by creating two arrays that only contain NaNs. Recall that when we plot NaNs, they simply don't appear on the plot, which is what we want. Then we're going to fill in the values corresponding to the state the values belong to. That is, all the values belonging to state 0 will go in one array, and all the values belonging to state 1 will go in the other array. Then, when we plot them at the same time, only one of these will have a value at each time step, and the other will be NaN. This will result in each of the states being a different color. Okay, so first, we're going to create two arrays called returns 0 and returns 1. Of course, these both have to be the same size as z. Next, we assign NaN to each of the arrays for each value. Next, we fill in returns 0, but only for the time steps where the state actually is 0. To do that, we can index return 0 using z == 0. As you recall, z == 0 returns a Boolean array of trues and falses. You can try this in your terminal if you don't believe me. Of course, it will be true when z is actually 0 and false otherwise. When we index return 0 with this Boolean array of trues and falses, we get back only the values where the index is true. Again, you can try that yourself in the terminal. On the right side, we do the same thing, but with the original returns. So in conclusion, what does this do? It assigns the returns from the original array to the new array, return 0, but only on the days where the state is equal to 0. Next, we do the same thing, but for returns 1 and where the state must be 1. Therefore, whenever returns 0 has a value, returns 1 is NaN, and whenever returns 1 has a value, returns 0 is NaN. Next, we plot return 0 and returns 1. We also call plt.legend, so we know which color is state 0 and which color is state 1. Okay, so let's run this. So we see that blue values correspond to state 0, whereas the orange values correspond to state 1. It's also easy to assign meaning to these states based on what we see. Clearly, the orange values are larger and the blue values are smaller. Therefore, we would say that state 0 corresponds to low volatility and state 1 corresponds to high volatility. However, notice that the values do seem to jump around a lot, especially when we are in state 1. When we are in state 1, sometimes we don't stay in state 1 for very long. And sometimes when we're in state 1, we alternate quite a bit between blue and orange. Now, we have to ask, is this the behavior that we want to see? Does it make sense if the regime changes every single day? That's probably not the case, since we want volatility clustering, not volatility fluctuations. In the next step, we're going to look at the state transition matrix, which will provide more insight. This can be done by calling the transmat attribute of our model. So these results should make sense given what we've learned. First, we can see that the probability of going from state 0 back to itself, which is located at the index 0, 0, is about 75%. This is the largest number in this matrix. That makes sense because the longest runs we see in our time series of stock returns is when the stock returns stay in the low volatility state. That is, the probability of going from low to low should be large. Now let's consider the probabilities in the second row. The probability at index 1, 0 is the probability of going from state 1 to state 0. The probability at index 1, 1 is the probability of going from state 1 to state 1. That is, from high to low and from high to high. Both of these are approximately 50%. So does that make sense? It does make sense because that's what we were seeing earlier. We saw that when the state goes high, it often switches back to low very quickly. That is, we have an even chance of going from high back to high or from high to low. So this makes sense for two reasons. First, when we look at our time series, we see that the periods where the state is high are generally very short. Sometimes it seems like it's just a single value. Furthermore, this makes sense in the context of the plot we saw earlier, where we plotted z as a time series. In this plot, we saw that the thick areas corresponded to when the returns were large. Now it makes sense why these lines are so thick. It is because they correspond to going back and forth between 0 and 1 very quickly. In other words, the reason why this line appears thick is because we are zoomed out so far that all we can see is a blue area. But in fact, if we zoomed in, we would see the state rapidly moving from 0 to 1 and vice versa. This is opposed to when we are in the low state, where the value just stays at 0. Okay, so this makes sense in terms of our Gaussian mixture model. Basically, the high value returns belong to the high state, and the smaller returns belong to the low state. These can change rapidly, as you saw. This makes sense. Just because today's return was very positive or very negative, this doesn't guarantee that the returns will be just as large tomorrow and the next day, and so forth. Instead, what we might expect to see is that we have a lot of very positive or very negative values over a period of many days. But this does not mean that the returns will be very positive or very negative every day. So I hope you understand the difference. To be in a high volatility regime does not require that the return is very large every single day. It only means that the return is large overall for many of those days. In other words, if we really want to detect regimes, perhaps we don't want the states to switch so often. In other words, we don't want to see high, low, high, low, high, low like what we are seeing here. Another way of saying this is that it might make more sense if the high volatility regime lasted longer and allowed for a few smaller returns. So what's one way we can model this? One thing we can try to do is to set the state transition matrix manually. As mentioned in the theory lectures, you can also try to label the data yourself and then calculate the transition probabilities using counting. In any case, what we are doing now is just a test to help us understand the behavior of an HMM. So what we are going to do is set the state transition probability of staying in the same state very high for both states. We would expect that by doing this, we will make switching states so unlikely that it won't happen very often. Okay, so now the probability of going from high to high is 99.9%, and the probability of going from low to low is 99.99%. The next step is again to call model.predict to retrieve the most likely sequence of hidden states. Next, we create the same plot as before, where we plot the hidden state sequence as a time series directly on top of the original stock return time series. So now we see what we expect. Now there are very few transitions between states, and the model prefers for the state to remain the same. Also, it's clear that the model does a good job of identifying the difference between large returns and small returns. In this case, state 1 refers to the high volatility regime, and state 0 refers to the low volatility regime. Remember that state 0 and state 1 don't have any meaning until we assign them meaning. Z would be just as valid if the zeros and ones were reversed. Okay, so this makes sense. By changing the state transition matrix to have more extreme probabilities, we make it so that switching between different states is more improbable, and this makes the sequence of states more stable and more plausible. Next, we draw the subsequent plot that we had before, where we color-coded the time series of stock returns according to their state. Since I've already explained this code, I won't do so again. So what do we see? So I think this plot looks a lot better than what we had before. This is another way to confirm that the states are more stable, and it's also clear from this plot what we would call a high volatility regime and a low volatility regime. Clearly, being in one state leads to much larger returns overall, and being in the other state leads to much smaller returns.